Very good. So we wait a little bit until we have a reasonable number of people. Yes, so we wait a bit. It's 14 hours and 1 or 2 minutes more until people finish lunch and decide to join. Welcome to this session. In 1 or 2 minutes we start. We decide to name this session Distributed Systems. It's while there are different papers that I hope we managed to find a common theme. So since the time is short, I think it's time to propose. Donc, the first paper of this session is about a unifying framework for deciding synchronizability. There are 6 authors, and I think the video is presented by Amrita, who gave also the teaser in case you haven't seen it. So you can start the video by Amrita Suresh.
Good afternoon. My name is Amrita, and I'm here to present the paper, A Unifying Framework for Deciding Synchronizability. This is joint work with my advisors, Benedict Bolig and Elan Finkel, and our colleagues from Nice, Cinzia De Giusto, Leticia Leversa, and Etienne Lowe's. FIFO systems are ubiquitous in the field of distributed computing. They have applications in communication protocols, session types, verifying concurrent programs, and so on. Essentially, they are distributed processes such that each process is a finite state machine. There are a fixed number of such processes, and they communicate using queues or channels with the first in, first out policy. We consider 2 types of communication architectures. The first being the peer-to-peer type, where there is one queue every pair of processes, and the second being the mailbox, where there is just one queue for every process. Let us look at an example. In the given example, we have 3 processes, P1, P2, and P3, and channels between them. Observe that we do not write the channels between P1 and P3 because in this particular example, there is no communication between these 2 processes. Next, we see that in the first process, the first process sends message A to process 2. So the sending is denoted by an exclamation mark followed by the message itself, and the reception is denoted by a question mark followed by the message itself. Let us look at a sample run. Now, first process 1 sends message A to process 2 and stays in the channel. On the right side, we have what is called the MSC, or the message sequence chart. Each vertex in a message sequence chart, in this case E1, is called an event. So all the processes are denoted by vertical lines, and every vertex is called an event. For the peer-to-peer model, given two events A and B, we say A happens before B if A and B are from the same process and A precedes B. We also say A precedes B if A is the reception, if A is the send to a matching reception B. Furthermore, for mailbox, we have the added constraint that if one of the events is matched and the other is unmatched, and they both send to the same process, then the matched event must happen before the unmatched event. Now, getting back to the example, we have E1 and a dashed arrow to process P2. The arrow is dashed because the message is not yet received. Next, we have process P2 sending the message B to process P1. So now B happens with a dashed arrow as well. Next, process P1 receives the B. So now the channel is empty and the line becomes solid. Similarly, process P2 sends C to process P3, which is then received, and process P3 sends D to process P2, which is then received. The execution is written as below, and it's called also the trace. And notice that even at the end of the execution, A is not consumed by the process P2, so it stays in the channel, and the line remains dashed. So we say a send is matched if there is a corresponding receive, and in this case, this send is an unmatched send. Now, look at the same example of the MSC for a mailbox system. It is still a valid MSC, but the trace is not valid because in the previous trace, we first sent message A and then we send message D later. But this is not possible because if we send message A to P2, since there is only one channel, A will be at the head of the channel, at the front of the channel. And if D is ever sent to that channel, it will not be received until A is received. But for the same MSC, which obeys the same happens before relation, we can have another trace, which is in this case, sending message B first, then sending message C, then receiving the message C, sending the message D, and then sending the message A, receiving the message B, and receiving the message D. Now, the main question that we're looking at is the boundedness problem, which says, is there a bound on the size of the queues for every run? Now, in general, this problem is undecidable. This gives way to studying under approximations. The most obvious under approximation we can consider is restricting all the channels or queues to a bound K. But this is too restricting as we cannot have unbounded runs then. So a slightly more general option is to have every unbounded execution being equivalent to a bounded execution, equivalent in some sense. Now, this kind of under approximation has been studied in the literature. The first being existentially K-bounded systems, where the constraint is that all accepting executions should be able to be reordered into a bounded execution. Another model that was studied is synchronizable systems, where the send projection of every execution should be equivalent to a send projection of something that is obtained by a rendezvous communication, which is communication in the absence of a buffer. And finally, most recently, K-synchronizable systems have been studied, which asks for every MSC to admit at least one linearization that can be divided into blocks or exchanges of at most K messages. We will look at this a little bit more closely now. So a K exchange is essentially an MSC that allows one to schedule all the sends before all the receives. And it's a K exchange, so we want there to be at most K sends. Now, any MSC that can be broken down into MSCs where a concatenation of MSCs where each sub MSC is a K exchange is called weakly K synchronous. For example, in the figure given below, each of these can be broken down M1, M2, M3, and hence it's a weakly one synchronous MSC. Next, we introduce a slightly more general model, which is just that an exchange where we remove the restriction on the number of messages, number of sends per exchange. So an exchange is an MSC that allows one to schedule all the sends before all the receives. And an MSC M is weakly synchronous if it's of the form M1 to Mn, where concatenation of M1 to Mn such that each MI is in just an exchange. So in this case, if you look at this family of MSCs, for every K that you consider, you can have K plus 1 sends in each exchange. For example, so the first one is the first message M1 is just a one exchange. But if you look here, we can have many M2s followed by an M3. And so this is an exchange, but it's not a K exchange. And finally, on the right, we have an MSC, which is not a K exchange or an exchange for any K. So if you observe, message M0 is sent and received. So everything that happens in the interim should belong to the same exchange. However, M1 is received and only after the reception is M3 sent. So we have a send receive constraint. So they can never be all the sends for all the receives. So indeed, this is not a K exchange for any K or an exchange. Now we talk about the framework of our paper. Our framework says that if any class of MSCs satisfy two conditions, then inclusion into that class is decidable. So what are these two conditions? The first condition is that the class of MSCs should be MSO definable. MSO logic, or monadic second order logic, is a fragment of second order logic where the second order quantification is limited to quantifications over sets. Now the set of MSOs formulas over MSC is given by the following grammar. So we have X and Y, which are first order variables, and they're interpreted as events of an MSC. And capital X here is a second order variable, which is interpreted as set of events. Now we have two relations. The arrow mark indicates the process order, where X precedes Y in the process order. And then we have the message order, where X and Y are matched send receive events. So the abbreviation matched X is written as exists Y such that X is always matched with Y. This indicates that X is a matched send. The second condition is that the set of MSCs have bounded tree width. Special tree width or tree width is a measure of how close a graph is to a tree. And in order to verify this for the set of MSCs, we play a decomposition game, where essentially Eve's objective is to color all the events, all the connected events with different colors. And every time she marks or colors any event, she can remove the edges between marked nodes. And Adam, when it's Adam's turn, he chooses one of the resulting connected components. And Eve wins if she can color or mark all vertices with at most K color, K plus 1 color. And if she can do that, we say that the graph or the MSC has a bounded special tree width of K. Now, the framework hinges on the crucial observation that if a class of MSCs is MSO definable and has bounded special tree width, then inclusion into that class is decidable. That is, given a communicating system S, all the MSCs of all the executions of that communicating system belong to the class of MSCs is in fact decidable. And how we go about showing this is that this problem essentially reduces to a bounded model checking problem, which was shown to be decidable. So you can refer to the report by Benedict Boleg and Paul Gaston, which talks about the same thing. Now let's look at the example of a framework and how we apply it. So we show that the set of weakly synchronous MSCs are MSO definable. So the first step is to show that they can be expressed in MSO logic. So to show that, we first construct the conflict graph. So given an MSC, we can construct a unique conflict graph, which talks about the relations between messages. So for an MSC, we have the happens before relation, which talks about relations between events, but a conflict graph talks about relations between messages. So for example, in the given conflict graph, we have 4 messages, A, B, C, and E. Now, A is sent before B is sent. So A precedes B with an SS dependency. Similarly, A is received before E is sent. So A precedes E with an RS, receive send dependency, and so on. And we have that the set of weakly synchronous MSCs are MSO definable because the graphical characterization of weakly synchronous MSCs is that there is no RS edge along any cycle in the conflict graph, and this is MSO definable. So because this property is MSO definable, we can indeed use MSO logic to define the class of weakly synchronous MSCs. Next, to show that they have bounded special tree width, we have a winning strategy for Eve. The winning strategy is to isolate each exchange and then remove the messages in pairs. And she can do this using at most 4n+1 colors. Let's look at an example. So here we have 2 exchanges. The first exchange considers only message A, and second exchange considers all the other messages. So the first step for Eve's winning strategy in 4n+1, where n is the number of processes. So we have 9 colors for a winning strategy for Eve in this case, but we will use lesser. The first step is to isolate each exchange. So she starts with the first exchange and isolates them. And you need 2n colors for this because you need to isolate the last event of the first process and the first events of the next process. So she marks these. And now we remove the corresponding edges. Now Adam has to choose one of the resulting connected components. He trivially loses if he chooses the red isolated vertex or the green one. So he chooses the largest connected component. Now, these 2 colors can be reused by Eve because now they don't belong to this connected component anymore. Now in Eve's turn, she again separates this from the rest of the MSC. And furthermore, she marks the first receive along every process. So in that case, this is already marked by red, but she marks this vertex. And she also marks the last send. So in this case, that is this one. And this is already marked. So now that she's marked the first receive, she chooses she chooses a linearization. So in this case, it's B, C, D, G, F, E. So she chooses the first vertex in the linearization and she tries to isolate that. So sending of B is the first one. So to this end, she uses an extra color and marks C. Now B is isolated and we have this left. Her next step would be to isolate the corresponding receive. So she marks that and that's isolated. Now we are back to the first position again. Now we again have the end vertices marked and we mark the next vertex after the first end event. So it's this one. And we isolate yellow and so on. So using this framework, we have been able to verify the inclusion for various classes. And for weakly synchronous, in fact, we have a better complexity. We have X time for mailbox because we use LCPDL instead of MSO. However, it's interesting that for the peer-to-peer case, it is actually undecidable. And we show this by reducing it to the post-correspondence problem, reducing the post-correspondence problem to this. And for weakly synchronous, which has already been studied, we can use the same framework for both peer-to-peer and mailbox. Then we introduce a strongly case synchronous model, which is a subclass of weakly case synchronous, but more intuitive in definition. And it is also decidable for that, and so on. Furthermore, we also have a comparison between all these various similar yet somewhat different notions. And it's interesting to see that for the peer-to-peer case, weakly case synchronizable actually belongs to existentially bounded, whereas for the mailbox case, actually incomparable. And so we have various other results as well. And to summarize, this framework basically tries to unify all the notions of synchronizability, and it actually can be used for any class for which we have MSO definability and bounded specificity with, and it's applicable to both mailbox and peer-to-peer communication. And for some cases, like I mentioned, for the weakly synchronous case, we can even use LCPDL for better complexity. Thank you.
Thank you, Amrita. Okay, you can raise your hand or ask a question, a written question on the chat, on the question and answer, if you want to have if you have a question. While you think about asking a question, so all the authors are there. My question is about the model, the MSC, which is a special partial order model. Can you see using this technique to, I mean, in this model, you have this idea of sending and receiving messages. It's a very specific thing. Are you interested in seeing other models in which the partial order, like database transaction or weak memory models, is there any way of extending these ideas to other partial order models, or are you specifically interested in this peer-to-peer sending model?
So we've been mainly looking at it from the point of view of communicating distributed systems. So essentially the model that I described. But that's an interesting question. And I don't know, maybe Benedict will be able to shed more light on it because he has looked into MSCs a little more in detail. But from the point of view of this work, I don't think we've looked into any other type of communication.
Yeah, hi everybody. Yeah, I agree with Amrita. So this would be an interesting question. As soon as we have some sort of graphical representation of communication, we could potentially apply this approach. That is the tree-bit characterization, MSO definability, etc. So, for example, this would probably also work for Mazurkiewicz traces and this kind of.
Right, in which you don't have this notion of sending and receiving, which is a bit specific to your model.
Yeah. But as you say, the weak memory communication and things like that would be interesting. So any case where otherwise the problem would be undecidable, simple reachability questions would be interesting to look at. Yeah.
Okay, thank you. Any other question that you want to ask? No question on the. No hand raised. Okay, so anyway, thank you very much, Amrita, for the talk. It was well organized and well presented, and the teaser was very nice. I knew what you were talking about, so it was, you played the game of the teaser very well. Not everybody did that, but thank you. So I think we move to the next talk, which is presented by Bastien and is about Gerd Automata for the verification and safety and liveness of distributed algorithm. So this is a talk about liveness and also using domain theory. So I like that paper very much, and I'm looking forward to the presentation by Bastien.
I'm going to show you how distributed algorithm can be verified using Gerd Automata. So this work was done by myself, Bastien Thomas, as well as Nathalie Bertrand and Joseph Wider. So first I will introduce what type of distributed algorithm we want to verify. So here I show an example of such an algorithm. It's inspired by the Face-King algorithm by Berman and Gary. And it's a consensus algorithm, meaning that it's run by n processes in parallel, and each process has a preference value, v, either 0 or 1, and at the end of the algorithm, all processes must agree on the same value. There are other conditions that I will not detail here. And an important point is that some of these processes are faulty. In this case, we consider a Byzantine fault, meaning that they can execute arbitrary code, and the algorithm must still be resilient to this. So how does this particular algorithm work? There is a sequence of instructions that is repeated in a loop. In this case, the loop is repeated t plus 1 time, where t is the threshold of Byzantine fault that can be tolerated. And the idea behind the algorithm is that at each iteration of the loop, all processes broadcast their current preference value, and if there is a clear majority, so n over 2 plus a threshold, then they update their preference to this majority, and if not, then they update their preference to king of to the preference of a king. In this case, the king is chosen such that its ID corresponds to the iteration of the loop. So what are the properties of such algorithm? So first, it's parameterized, meaning that it's not run by a fixed set of processes, but instead the number of processes involved is a parameter of the algorithm. There are also other parameters such as threshold of tolerated fault. It's also non-deterministic. So in this case, non-determinism is caused by Byzantine faults. So this particular algorithm is synchronous, but we would like our method to work just as well for a synchronous system. And finally, there are unboundedly many rounds. So in this case, it's unbounded because it's a parameter t, but there are other cases where it can be even infinite, simply. So this will be what makes this procedure more difficult. So in order to model this system, we will introduce a new notion called layered threshold automaton. So a threshold automaton, there has already been some works done in this setting, but our method differs from a classical threshold automata in a different way. So the states of layered threshold automaton, there are infinitely many of them, and they are arranged in layers, so indexed from 0 to infinity. So in this case, state of an LTI, I'll use shorthand, means a local value, a local state of a process. So for example, the state V0 and V1 in layer 0 means correspond to processes that have their value of the variable V set to either 0 or 1. The state K0 or K1 represent the same thing, so value V equals 0 or 1, but additionally, a process that is in such a state is considered the king of the round. So then a process will move through different states, through different layers towards its execution, and we record every state it has been through. And we do the same for every other process. And doing this, we obtain what we call a configuration, which is the path taken by every process through this LTA. So there is an additional step, because for now the set of process is fixed, and we don't want this because we want to perform a parameterized verification. And so we do what we call a counter abstraction, meaning that instead of recording for each process in which state it is, we record for each state how many processes are in it. And doing this, we manage to not explicitly define a set of processes, and this will make things easier for parameterized verification. So now, obviously, a process cannot move in any fashion from one state to another, and the way it moves is dictated by the code of the algorithm. So for example, here we have a condition on the number of messages 0 that were sent at a given layer. And in order to encode this constraint, we use a notion of guard, meaning that between each pair of states of successive layer, we will add a guard that corresponds to a formula over arithmetic. So here is an example of one. I will detail the role of each variable here. So the variable v0, so it's the same as the state v0, but in the context of formula, it encodes the number of processes that are in state v0 at the source layer. And then there are also parameters. So here n and t were already presented in the code of the algorithm and represent respectively the number of processes and the number of tolerated faults. And f is the actual number of faults that must be lower than the threshold. So doing this, we say the meaning of this guard then becomes that the number of processes that have v0 plus the number of potential Byzantine processes must be greater than n over 2 plus t. An important property of this guard is that they cannot become false during an execution. So I will justify this property later, but it can be used immediately with the following theorem. So this theorem allows us to characterize the set of accessible configuration. So it states that if a configuration like this is both flow coherent, meaning that the number of edges that leave a given state must be at most the same as the number of edges that enter it. So this encodes the fact that we do not create process. However, some process may still are in a state but have not yet progressed to the next one. And also guard coherent. So this means that if an edge is taken, then the corresponding guard must be satisfied. So this uses the fact that guard cannot become false, because if the guard could become false by taking later transition, then verifying it that it holds now would not have any meaning. But thanks to this property, this theorem holds, and this theorem would be sufficient in the case where the LTI would be is finite, because then every single condition here can be encoded as SMT formula, and if the LTI is finite, we obtain a finite SMT formula that can be checked automatically. In the case where the LTI is infinite, however, something interesting happens, because in this theorem there are no conditions on the finiteness of the configuration, meaning that there can be a configuration where a process has moved infinitely often. And traditionally, in this case, the traditional notion of accessibility is not sufficient, because usually we say that if there is a finite number of steps that allow us to reach this configuration, and in this case it would not be possible. But using domain theory, we managed to introduce a notion of extend this notion of reachability to include reachability with infinitely many steps. And if we consider this extended notion of reachability, the theorem still holds for infinite configurations, and it will allow us later to prove liveness properties. So now maybe it must be verified that the notion of LTA that we introduce encode precisely the semantic of a distributed algorithm. So to show this, we created a very concrete system, very precise, where not only do we record the state of each processes, but we also record the messages that each process have received from another process. So for example, when P1 was in V1 in the first layer, it sent a corresponding message, and in the array below, we record that P0 here has received a message from P1 at the very first layer here. And doing this, we can encode very precisely the guards of the automaton by transcribing exactly the guard of the algorithm. And we obtain something that is quite close to the semantic of a distributed algorithm. However, this model is quite complex to verify, and so we performed several abstraction steps on it to obtain something more manageable. So the first abstraction consisted simply in removing the buffer of received messages below. And doing this, we obtained something that we call the Succinct Configuration, which we introduced earlier. So it's exactly the above array is exactly the same as the flow system below. It's just presented differently. And what's interesting about this abstraction is that now the guards cannot relate to received message, but must instead concern sent messages. So in order to perform this transformation, we say that the set of received message at a point can be any subset of the set of sent messages. So in doing this, in general, we would add a lot of false execution. But because of the layered structure of the automaton, such is not the case, and this is represented by the blue dashed arrow. That means that any path between such configuration can be transcribed back into full configurations. So then the next step I've already presented is a counter abstraction. So we have the same thing here, meaning that both the abstraction arrow, red, and the concretization one, so dash blue one, are true, meaning that the abstraction is both correct and complete. But the problem with counter configuration is that there are still infinite in two ways even, because not only there are potentially infinitely many layers, but also every one of these counters can be arbitrarily big. And this makes things quite hard for verification. And so we perform one additional step, which is the guard abstraction. So we fix a set of guards, which are formula over the variables here. And instead of recording the exact value of each of these variables, we only record the valuation of this finite set of formulas over these variables. So here you notice that there is no blue dashed arrow going back, because this abstraction step is only correct and not complete in general. But still, in general, it will be, in practice, it will be enough for a lot of verification purpose. So doing this, we managed to have only finitely many possible columns, and it will come into play now. So I will present the Gerd Automaton. So first I redrawn the previous Gerd configuration. And what we do is that we consider each column of this configuration to be a separate letter. So in this case, we can see a guard configuration as an infinite word over the power set of the guard. And the power set of the guard is finite, which means we have an infinite word over a finite alphabet. And then capturing the reachable configuration is the same as the set of reachable configuration is the same as a language over of configuration. And this can be easily dealt with an automaton, which I will show here. So the Gerd automaton is defined as, so the state of the Gerd automaton or exactly the letter of the alphabet. So here, gamma 0 to gamma 4, and there are many others. And a transition between two states exists if it is possible for these two letters to appear one next to each other. This can be checked with an SMT query, and therefore the whole automaton can be built automatically in this case. And the important property is that then the set of all reachable configuration is a subset of the language of the automaton. So this procedure is only correct and not complete because we only have this inclusion and not the other one. But in practice, it will be sufficient to prove some properties over a distributed algorithm. So here, the algorithm I showed earlier was inspired by Faceking, but was in fact false. It didn't work. But we managed to find a quite simple Gerd Automaton for the real Faceking algorithm that is presented here. And it is sufficient to prove the liveness of this algorithm under the assumption that at some point a non-Byzantine king is chosen, so represented by a true on one of these two first formula. So this means that if we exclude the execution where we loop always on this state, then at some point we will arrive on a state where either v0 equals 0 or v1 equals 0, which is what we want to prove. So obviously, once we have built the Gerd automaton, the model checking become a traditional model checking system with a transition system. And so a lot more can be done in this way. So it is time to conclude the presentation. So in conclusion, what we did is we defined the notion of LTA, and we provided a clear link between the semantic of distributed algorithm and the semantic of this LTA. We also defined the Gerd automaton that can be built on such LTA and proved that this verification procedure is correct. There are still a lot of things that we can do in this setting. So the first one is related to abstraction refinement that can be used in other areas of domain checking. And we believe it can be used here as well, which would help in optimizing the construction of the Gerd automaton by selecting fewer guards, hopefully, and more clever ones. And another important point, but quite a hard one, is to add randomness to these models, because a lot of asynchronous algorithms that run on infinitely many rounds only terminate almost surely, and without adding probabilities, we cannot prove the correctness of this algorithm. So thank you for your attention, and if you have any question, I will answer.
Thanks to Bastien for this presentation. And I think he's around to answer questions, as well as Natalie. Anyone wants to ask? I cannot see open questions. Anyone raising their hands? No hands raised. So again, while people start thinking about what they want to ask, you mentioned again domain theory in the presentation just quickly. You don't use a lot of it, right? I mean, it's just the intuition that you can extend from finite chains to have an infinite chain, and then you say, okay, there must be a limit somewhere. Do you use other notion than chains? I mean, do you have directed sets? Do you need to find the limit of a directed sets, or use always linear executions, for instance, that you consider in this paper?
Do you hear me?
Yeah, I can hear.
Okay. So the domain theory is that it makes a lot of things nicer. So typically the abstraction steps that I presented earlier, the main argument of the correctness is the Scott continuity
Okay.
of the red arrows of the abstraction. But in terms of what I use in domain theory beyond the Scott topology, it's true that for now I don't use a lot more of it.
But I mean, the question was, you have always limits of chains, right? I mean, do you have execution that are directed sets or that have more structure than just chains?
Currently, no. I only consider chains.
And omega chains. I mean, you don't go beyond the omega, right?
I
You
don't use a more fancier.
could you imagine computations that go beyond omega? Could that be interesting to have more transfinite notion of computation here?
It's true that there is something we can, for example, imagine an execution, but I don't know what it would translate in reality, where a process takes infinitely many steps and then takes another one.
Yeah, but the Zeno processes do that, right? I mean, you have an infinite things and then you finish and then you start again. I mean, I don't know if it's realistic, but anyway, yeah. You still don't have.
It could be possible to model it, but I don't have any application in mind where this can be used.
And how far are you in the implementation of this procedure so I mean, you want to program a tool, right?
Yeah, so now the automaton I showed was created automatically.
Okay.
But the guards are inputted by hand still because we don't yet have a way of automatically computing them.
Okay.
And yeah, the automaton is built automatically once we provide the guard.
Okay, so and you are going to present this tool in another place, right? Yes, possibly.
Possibly, yes. Hopefully.
Okay. So again, no more questions, I suppose. Nobody is curious to know more. Well, thank you, Bastien, for this.
Thank you.
And so the last paper in this session will be presented by Umang Mathur, is about dynamic data race detection through the fine-grained lens. So this is also a subject quite interesting. There is no teaser for that, so we don't know what this paper talks about, and we are all curious to find out during the presentation. So you can start the presentation by Umang.
Hi, I'm Umang Mathur, and I will be talking about our work on characterizing the fine-grained complexity of dynamic data race detection. This is joint work with Rucha Kulkarni and Andreas Pavlogiannis. Today, most large-scale software applications directly or indirectly use concurrency to achieve performance and overcome the limitations of Moore's law. However, reasoning about even small concurrent programs become intractable owing to the interleaving explosion problem. As a result, concurrent programs are very challenging to develop and maintain, and concurrency bugs repeatedly make their way into production level software. Amongst all kinds of concurrency bugs, data races are the most common ones. Data races are hard to detect, reproduce, and are often symptomatic of even bigger problems in the code. As a result, over several decades, computer scientists have developed techniques to detect data races in concurrent software. Amongst these techniques, the class of techniques to detect data races dynamically are the most common. In these techniques, instead of analyzing the entire source code, one looks at a single program execution and tries to infer the presence or absence of a data race from that execution. Data races has been actively studied for over 5 decades now. Over the years, several notions have been developed together with techniques to check them. In the initial few decades, the efforts were focused on developing simple yet foundational techniques like the use of the happens before partial order. In the next decades or so, researchers developed race detection techniques based on explicit or symbolic enumeration. Finally, in the past few years, there has been a rising interest in coming up with more practical techniques that infer data races and reorderings of observed executions. As practical software applications that deploy concurrency are typically large and generally execute with more than hundreds of millions of events, the dynamic analysis techniques that scale in practice are mostly those that take time that is linear in the size of the trace. In other words, they look for those kinds of races in executions that are linear time checkable. In this work, we consider some of these linear time checkable notions and investigate their complexity theoretic limits. With this, let us delve into some technical details. In the context of this talk, we will focus on executions of concurrent programs. Such executions can be thought of as sequences of events. The example execution on the right has 6 events, and these are performed by 2 different threads, T1 and T2. So every event tells you which thread performed that event and what is the operation performed by that event. See, operations are either memory accesses, that is, they write or read from memory locations, or they are acquires or releases of locks. In this work, we are interested in complexity theoretic questions. In this context, execution traces will be inputs, and the size of the input will be the number of traces, number of events in the trace. There are other parameters of the input trace which will also play a role in the complexity of checking data races. These are the number of threads, number of logs, and the number of variables. Let us now formally define data races. An execution is said to have a data race if there is a pair of conflicting events in that execution that are concurrent. By conflicting events, I mean 2 events that access the same memory location, are performed by different threads, and at least one of them is a write. The notion of concurrency depends upon the precise notion that we want to check. So the problem of dynamic data race detection then asks if an execution has a data race according to some chosen notion of data race. We next describe some popular notions for data races, which we also consider in our work. The first and one of the most popular notion is that of happens before races. Happens before is a partial order over the set of events of a given trace. Intuitively, it orders events in a given thread as follows. So in a given thread as they appear in the trace. Further, HB orders critical sections on the same lock by ordering the release of an earlier critical section before the acquire of the later one. An HP race is simply a pair of conflicting events that are not ordered by the HP partial order induced by the trace. In the trace on the right, the 4th event and the 9th event are conflicting and are not ordered by HP. Thus, they form an HP race. HP races can be detected using a vector clock algorithm that runs in time n into t. So n is the number of events and t is the number of threads in the trace. The other popular notion of data races is related to the lock set principle. This principle says that conflicting accesses must always be protected by a common lock, and non-adherence to this principle can potentially lead to data races. So formally, a lock cover race is a pair of conflicting events such that the set of locks acquired when executing E1 and E2 are disjoint. The existence of a lock cover race can be detected in time n square L by examining all pairs of conflicting events. A more practical notion based on the lock set principle is that of a lock set race. Intuitively, a trace has a lock set race if there is a variable x such that there is no single lock that protects all accesses to x. In the trace on the right, there is no lock cover race, but there is a lock set race, as there is no common lock that protects all accesses to the variable x. The existence of lock set races can be checked in time that is linear in the size of the trace. So amongst other things, we show in this work that lock cover races are theoretically harder to detect than lock set races unless some well-believed complexity conjectures fail to hold. Finally, we consider a relatively new notion of data races, namely that of synchronization preserving races. Intuitively, a trace has a synchronization preserving race if it has a synchronization preserving reordering that witnesses the fact that some 2 conflicting events are in race. Informally, a synchronization preserving reordering of a given trace sigma is a trace that preserves the intra-thread ordering and the control flow of sigma, and further does not flip the order of critical sections on the same lock. So on the right we have a given trace sigma, and this is the synchronization preserving reordering of sigma, and in this reordering the write x and the read x is is exposed as a data race. So the initial trace has a synchronization preserving data race. This notion of races was introduced in a recent Popple paper and was shown to be strictly more powerful than HP races, and it was further shown that it can be detected in time that is linear in the size of the trace and respectively linear and cubic in the number of variables and threads respectively. So all the notions of data races that we just recalled can be checked in linear time. That is in time that is proportional to the number of events in the input trace. However, the precise running times of these algorithms for detecting each of these notions depend on other parameters such as threads, locks, and variables in a multiplicative fashion. Some of the algorithms have a higher degree of dependence as compared to some others. But when deploying algorithms for race detection in real-world scenarios, these parameters cannot be assumed constant, and most of the times they can be a major impediment in performance. The central question we ask in this paper is, can we design purely linear time algorithms for the popular data race notions we consider? If not, can we prove impossibility of the existence of these purely linear time algorithms? So in this work, the notion we consider a different class of reductions. So the notion of the canonical polynomial time reductions in traditional complexity theory will be insufficient to show the unlikelihood of linear time algorithms. Instead, we resort to fine-grained complexity theory in this work, which advocates the use of a more refined notion of reduction called fine-grained reductions. So let us formally describe these. Let A and B be decision problems, and let P and Q be functions that map input sizes to running times. Then we show that the problem A PQ reduces to the problem B if informally an algorithm that runs faster than time Qn for B implies an algorithm for A that runs faster than Pn time. This is formalized by saying that for every epsilon greater than 0, you can find a delta greater than 0 and an algorithm RA that solves A in time P of n raised to 1 minus delta on inputs of length n, such that RA makes k oracle calls to B with inputs of lengths n1 through nk, and the following inequality holds. This inequality says that if there is an algorithm for B that runs slightly faster than Qm on inputs of length m, then the total time spent in the oracle calls is at most the time spent by RA outside of the oracle calls. Notice that the notion of reductions is very expressive and encompasses all traditional notions such as Turing, ConcurRent, or truth table reductions. In our work, we refer to many widely believed complexity theoretic hypotheses about specific computational problems, and we show fine-grained reductions from these problems to the problem of data race detection. So let me describe two of them here. The first hypothesis is the strong exponential time hypothesis, or SET for short. Intuitively, it says that there is no sub-exponential time algorithm for SAT, not even a randomized one. The next hypothesis is the orthogonal vectors hypothesis, and it says, and it sort of conjectures the hardness of the orthogonal vectors problem. So the input to the orthogonal vectors problem is two sets A and B, each of size n, containing d-dimensional bit vectors, and the task is to determine if there is a vector x in A and another vector y in B such that the dot product of x and y is 0. The naive algorithm for answering the OV problem enumerates all possible pairs of vectors and checks their dot products, and this runs in time proportional to n square. So the OV hypothesis states that there is no better algorithm for this problem. In fact, it has been shown that the OV hypothesis is computationally equivalent to SET, as there is a fine-grained reduction between the two. With this, let me summarize the contributions of our paper. Recall that the input to all the different problems we consider is a trace with n events, t threads, l locks, and v variables. In this paper, we studied the fine-grained complexity of checking data races according to different notions of data races, namely happens before, lock set principle, and synchronization preserving races. Recall that when the number of threads, locks, and variables are constant, these notions can be checked in linear time in the size of the trace. In our paper, we first show an improved upper bound for detecting HB races. We then show that the problem of checking if a trace has a read-write HB race is quadratic hard, conditioned upon the Seth hypothesis. We next show that for the general problem of checking the existence of any HB race, we show that Seth-based lower bounds are likely to be not meaningful. Finally, we show a lower bound of n raised to 1.5 by reducing from the problem of model checking against first order sentences with quantified prefix for all x's. An algorithm for race detection that runs faster than this will imply major breakthroughs in complexity theoretic questions pertaining to model checking of first order logic. We then consider the problem of checking lock set, lock cover, or synchronization preserving races and show similar improvements or hardness and impossibility results for them. We refer to our paper for details of these results. In this talk, I will discuss two of these results in detail, and these are results about happens before races. So recall that the HB partial order is defined over the set of events of a given execution when they are in the same thread or their releases and acquires on the same lock. Further, an HB race is a conflicting pair of events that. Let us consider the problem of checking the existence of an HB race. One can model this problem as a graph theoretic problem. The vertices of the graph are events in the execution trace and the edges are immediate HB orderings. This graph is sparse as the degree of each vertex is at most 2, and thus the number of edges is at most double the number of vertices. Now, if we want to check whether a given pair of conflicting events even E2 is an HB race, we can do so by performing a graph search in order n time. On the other hand, if we were to check the existence of such a pair, we can perform order n graph traversals taking a total of order n square time. There is also a vector clock algorithm that performs this task in order n into t time. Now we want to understand if there is a better algorithm. That is, in particular, we want to check if the existence of HB races can be performed in order n time without any multiplicative dependence on any other parameter. Our first result is a new algorithm that checks for the existence of HB races in a trace in time order n into L, where n is the number of events and L is the number of locks in the trace. The algorithm computes what we call lock stamps for every event. A lock stamp is essentially a mapping from locks to integers. You can perform different operations on lock stamps, including updating the value of a given lock, pointwise maximum, minimum, and comparison of two lock stamps. Each of these operations take order L time. In our algorithm, we assign two lock stamps to each event, an acquired lock stamp and a release lock stamp. These assignments satisfies the following property. If event E1 is ordered before E2, then the release lock stamp of E2 is not smaller than the acquired lock stamp of E1 according to the pointwise order in lock stamps. Let us quickly look at an example trace and the lock stamps you assign to the events in the trace. The acquired lock stamps are assigned in a forward pass. The first event Wx is assigned the lock stamp 00. This means that there is no acquired event of lock L or of lock M that is HB ordered before this event. Then the acquired lock stamp of the next event acquire L can be computed as follows. Its value is 10, denoting that there is one acquired event of lock L that is HB before this event and no acquire of lock M that is HB before this event. Likewise, the lock stamp of the third event is also the same. Similarly, the lock stamp of the fourth event is 20 and that of the sixth event is 21 because there is one acquired event of M that is HB before the sixth event. The release lock stamps are assigned in a similar fashion, although in a reverse pass. Notice that event 1 is HB ordered before event 10. Further, as expected, the acquired lock stamp of E2 is not ordered before the release lock stamp of E1. The summary of our algorithm is based on the following observations. First, as we saw before, a lock stamp assignment can be used to infer the HB order between any pair of events. Second, we can assign acquire and release lock stamps in time n into L. Third, we observe that instead of checking HB relationship between all n square many pairs of conflicting events, it suffices to check for an HB race only between order n many pairs of conflicting events, which we call consecutive conflicting pairs. These are pair of conflicting events such that there is no other conflicting right event E3 that appears between E1 and E2. Finally, there is an order NL algorithm that checks the log stamps of these order n consecutive conflicting pairs of events and determines the existence of an HB race. All of these 4 observations are sufficient to show that the overall algorithm runs in time proportional to the order to n into L. We now turn our attention to proving a quadratic hardness result. Our hardness result is for the problem of checking if a given input trace has a read-write HB race. That is, a pair of conflicting events E1 E2 such that E1 and E2 are unordered by HB and either E1 or E2 is a read event. We show a fine-grained reduction from the orthogonal vectors problem. Recall that an instance of this problem is 2 sets A and B of n bit vectors each on d dimensions. And the output is yes if and only if there is a vector x in A and a vector y in B such that the dot product of x and y is 0. Recall that the OV hypothesis states that the problem cannot be solved in time that is better than n quadratic n square in the n square and polynomial in D. Our reduction constructs a trace from the given OV instance. This trace is constructed by concatenating smaller subtraces, one for each of the vectors in the set A, followed by subtraces corresponding to the vectors in B. The subtrace corresponding to each vector x in A is constructed as follows. The subtrace has a single write event on variable z. Further, for every dimension I, there is a thread indexed by this vector and the dimension I. We add synchronization events to ensure that the write z event is HB ordered before the first events of each of these threads. Next, for every dimension I that is 1 in the vector, we add a critical section on log Li in the thread corresponding to I. Finally, if x is the last vector in which I is 1, then we also add critical sections on m logs. These m logs are indexed by vectors in B and the dimension I. Let us now look at the subtraces corresponding to a vector y in B. Each of these subtraces contain a single thread indexed by this vector. The last events of these threads is a read event on the variable z. Prior to this read event, we add critical sections on logs m corresponding to those dimensions that are 1 in this vector. The correctness of the construction relies on the observation that the write event corresponding to vector x is HB ordered before the read event of vector y, if and only if there is a dimension j such that both xj and yj are 1, and thus x and y are not orthogonal. In this construction, we use nd threads and logs, a single variable, and order nd events. The time to construct this trace is also nd. Finally, we observe that this is a fine-grained reduction if the existence of read-write HB races can be detected in time nd raised to 2 minus epsilon, that is subquadratic in the length of the trace, then we can also solve OV in the same time, thus violating the popular OV hypothesis. With this, let us recap our results in the context of HB and gauge where we are in terms of precisely characterizing the complexity of happens before race detection. First, it was previously known that the existence of an HB race can be determined in time nt. We improved this time bound by presenting another algorithm that works in time n into L. We then showed that there is a quadratic lower bound for the problem of checking HB races, which are read-write races, by showing a reduction from OV. In our paper, we also show that Seth is unlikely to yield any interesting lower bounds for general races. And we also use another conjecture on the complexity of model checking first for all exists FO sentences to show n raised to 1.5 bound for this problem. With this, I will summarize our contributions as follows. We consider the problem of dynamic data race detection and establish fine-grained complexity results for several notions with data races, most of which are checkable in linear time when trace parameters such as number of threads, logs, and variables are considered constant. There are several interesting avenues for future work in the intersection of dynamic race detection and complexity theory. The first and the most intriguing direction is to settle the complexity of checking HB races and determine if there is a quadratic lower bound, and if not, can we come up with a truly subquadratic algorithm. Next, we observe that all algorithms that are known for data races use space that is either proportional to the number of events or to the size of some parameter like the number of threads. Since space can be a huge bottleneck in most real-world applications, it would be interesting to come up with space and time efficient algorithms, or alternatively to understand the space and time trade-off. Finally, the use of randomness as a resource and how it can be traded with time or space is also an interesting avenue, both from a theoretical as well as a practical standpoint in the context of data race detection. With this, I would like to thank you.
Thank you, Mar. I seen you are around as well, maybe to answer questions.
Yeah.
Thank you. I don't see for the moment questions. Again, it's tricky to write them, but you can raise your hand and you can talk. We can promote you as panelist and you can talk. So you shouldn't be shy. You don't have to write, you can talk. But while we wait for people to overcome their shyness, so there is a lot of stuff in this paper. And one thing that I find hard to follow when I see this kind of work is a lot of the definition are because the model is very specific. You have locks, you have write and read, you have variables. These are very kind of notions. Can you imagine? So where I come from, I would define races as a confusion in event structures, right? And then you don't have to have a notion of write and read. You can have more abstract notions. Have you ever tried to consider models less, I don't know, which less details of that, in which you have a notion of race which can be defined more generally or more abstractly than write, read, locks? These are very programming notions. Have you ever tried that? Maybe.
So are you suggesting that we, so when you say, so I of course do not get the exact details that you're trying to talk about, but perhaps you want to talk about, let's say, just some form of partial orders and then trying to check.
I mean, you have a model in which you don't have notion of read and write and locks. These are very specific programming notions in which you have a programming language. Now,
That's
if
right.
I have a model in which I have less information about the original language who built the model, and then I have a more abstract notion of race. So I can suggest some, but have you ever thought about being less, because the proofs you have are very detailed in you. Okay, you have a right, and also the notion of race you define are depending on when you have two rights or one write and one read. I mean, maybe it would be simpler or more general to find proofs in which you have less of these details, and the proof would become more kind of the structure of the proof would become easier also to follow. I don't know, just.
Yeah, such I don't think we have a simpler notion. Do you have a suggestion?
Yeah, but well, okay, say patternets. You can consider, if you want a model of partial order which is very general, you have a patternets, and in patternets, races can be defined as typically symmetric confusion. And then, I mean, I suppose you could find a more general structure of the proof, because I mean, the proof you have in the paper are very ingenious. I like it, the way you present it, but are very tight to, I mean, if you change the model a little bit, you cannot apply them anymore. You see, that's kind of, I mean, it would be nice to, if you could do the same things to a more abstract model like patternets, for instance.
Yeah, so that's a good suggestion.
Just an idea.
Sure, yeah, that's a good suggestion. Although I think executions out of patternets are more like Mazurkiewicz traces.
Yes.
But they are rather, I mean, they're actually easy. The lower bounds will likely not apply to them. So anything that is as simple as like a uniform trace where every read write is ordered, it's likely going to be easy. So that's why you need more complex things like locks, which let you do mutual exclusion, and also reads writes where you're only ordering a read write when they're directly dependent. Like when a read reads its values from a write event, only then we order it. Otherwise, we don't order it. These are the sources of hardness. Otherwise, if it's just like a uniform partial order,
I see your point, but then the question becomes, can you describe in a more abstract way the structure of the partial order you get by these notions? Because you have this specific notion of locks and write and read, but you can abstract away from this by saying, okay, the structure of the partial order is such that, and then it would be a special case of a general order, or maybe a I mean, I would like to see something in which you don't have so much syntax, say. I'm just the way I come from.
Yeah, I understand. Yeah, right now we don't have anything like that, but that's a good suggestion. Thank you.
Anyway, I was hoping people would come out of their shyness while we were discussing this.
So maybe if while we wait for people to get some courage, maybe just a comment on that. I think that's an interesting suggestion you're making there. But typically when we work with lower bounds, if you make the model more complex, then you can only strengthen the lower bound in some sense. So, most of the paper is concerned with lower bounds, and a very rigid and simple syntax makes it harder to obtain such a lower bound. If the model was more convoluted, typically it would only make the problem of detecting data races harder. So
no, but not more convoluted. I would say more simpler, because it would be structure. You wouldn't have a notion of read and write. You would have just events and structures on the relation between the events. That's what my suggestion is.
Right. Okay. But
you see,
this still sounds more difficult to reason about, let's say, to me.
Possibly, yeah.
And that's why I would think that lower bounds would persist. But of course, this remains to be proven, and it's a good suggestion to go that way.
Anyway, I don't think people have our discussion have interested a lot of people, because there are no raised hands. There are no questions. So before we finish, I recommend you to go to Gather Town to socialize with other people. Maybe you find someone you know, and you just didn't realize he was participating in the session. And then, okay, but thank you to the authors and to the presenters for this session, and for the technical help of ConcurB, and see you at 15:45 for the keynote speaker.
Thank you.
Thank you for the link, Gather Town. See you later. Bye-bye.
Bye-bye.